I am Apurva Dhingra and I'll be taking a tutorial of Stochastic Control and Communication, week 6. Uh, if you recall, in the last tutorial, we talked about a few examples where dynamic programming could be used to find the optimal strategies or the optimal controls and the optimal value in those both situations. This time, this tutorial is going to talk about two things. One is what if we are not restricting ourselves to the case of Markov policies? Instead, we allow history dependent policies which are deterministic and also history dependent policies which are randomized. And the question is, are these even needed to talk about optimality in typical settings? Then we'll talk about another class of problems which is called, uh, in stochastic control, it is called with imperfect information, or in the language of MDPs, it is called partially observed MDPs or POMDPs. So these are the things that we're going to talk about. Are there any doubts from the previous class or the previous uh, tutorials so far? Okay. Let's go back a little bit. We know our DP algorithm. Okay, let's write it down. We have learned this much, that we can put these kind of problems in two classes, either stochastic control type problems or MDP type problems. These problems can be solved, as in we can find the optimal value and the optimal action or policy for them. Uh, and to do that, the typical process is to use dynamic programming or the optimality condition. So what it tells us ultimately is that there is this DP condition. We're again trying to, this is our goal in any of these stochastic control problems. We're trying to optimize for some expectation where the expectation is over the terminal cost and all the other costs in, say, the k steps. And here the inside is the xk, uk, and wk, where uk is the action, and we're minimizing over the actions or the policies that can be taken. So instead of writing it like that, let me write mu k of mu k. Let it be just that, it's the functions. So we are optimizing over these. So far what we saw was the situation where mu k was started from the space of action, the space of states, and we were getting some action corresponding to it, or rather this way. So it means that we'd start from some state xk. The policy would give us what should be the next action, or maybe we can write it as uk. And these types of policies were called Markov policies. I mean, these types of actions lead to Markov policies, where the policy would be all of these, mu 0 till mu whatever we're looking at, so n minus 1 here. This is Markov. Okay, so now we're going to talk about what happens if, instead of trying to reach this goal, the space of strategies that is allowed to us, or the policies that we can take, doesn't have to be restricted to Markov deterministic. We can actually take strategies which are beyond this. Okay, just notice I am using the word strategy to interchange with policy. That's all I'm doing here, nothing more. So there are other types of policies, right? There are history dependent policies, or there are history dependent randomized policies. We have already seen what these are. We even saw examples of these in the lectures and in the tutorials. So let's just take a quick recap of that. So history dependent means there will be some history h of t that basically would be starting from the state S0, the action taken there, the next state and the next action, till this set is complete, that we have seen the state, the previous state and the previous action, and reached the current state. So ST is also known, but the action that is to be taken is yet to be decided. That is what history means. And policies which are dependent on history would give ut to be of this form. We'd be taking from the set of histories, we'd be taking actions, but the action has to be only dependent on the last state. So ST is all it will depend on. Meaning mu t ht would be some ut, and ut will be something that belongs to the action space of ST, the last state that was seen. These are deterministic history dependent policies. Deterministic because our map gives us one particular action to be taken. On the other hand, the other possibility is if we start out from the space of histories and instead go to the simplex of the action space. I've not written the action space clearly here. I'll come back to this in a moment. This means that we'd start from ut of ht, and the resultant will be actually some probabilities. So it'll be some q that depends on the policy choice, and it leads to some action A. Because this is probability, it will satisfy the standard conditions on probability, that if you sum over all the actions A, this should be equal to 1. It should get normalized, or each of these individual values for every A has to be greater than or equal to 0. Those kind of standard things will be satisfied. So now if we were to talk about this Bellman equation, either the goal of the Bellman equation or the DP version of it that we saw earlier. So the DP version was, we start from Jn of xn and we just get the terminal cost there, that's nothing there, and we do backward induction and get the remaining terms. So it will be jk of some xk. This one is to minimize. Now the minimization is over only mu k, one step. So this looks at the stage wise cost, which is gk of this guy plus the j value or the Bellman value or just the value function from the previous case. So it's jk plus 1 of state xk plus 1. Here by default this uk was coming from some function mu k, some policy, and it was just dependent on xk. Similarly, here xk plus 1 is some function that defines the dynamics of the problem. Again, there is uk coming up, which comes the same way. So when we talk about the situation where we have history dependent policies, so these are the two locations where things will change. Okay, so to talk about that, we also need to talk about what happens to rewards. Will there be anything that changes? Or so if we define, if we are talking about the reward in this form, state comma current state comma action, not state comma action comma next state. That is also possible to do. That's just expectation using the transition probabilities. I'm not going there. So if we were focusing on reward like this, then in the case where we are talking about deterministic policies, that means this mu t of ht would give us one action, whatever that action is, and hence the reward will just be whatever that action is. So let's just call that action as uk. Okay, so this part is straightforward. Because our policy is deterministic, this gets replaced by uk, and that's our reward function. Nothing else needs to change over here. But when we are talking about the randomized case, remember the randomization now is over the actions. Each action is given a probability that I'll take action number 1 with probability half, maybe other action with probability half again. Something of that sort is being done. That's what our q is telling us, this quantity. Which means here, if we want to find out what is the reward for this particular policy, which is history dependent and randomized, we need to consider each of these situations. So I'm writing it this way. This quantity gives us the probability of getting the action u. For a particular action, it might be even 0, but it doesn't have to be always that. And then using r, basically taking expectation over all of these. Oh, yeah. If these are discrete, so we'll just take a sum over them. So sum over the u's. Okay so far? So what we have done is we're just trying to reach the same, we're just trying to convert our Bellman equation to the situation where instead of Markov deterministic policies, we had either history dependent policies which were deterministic or randomized. In those two cases, certain things are supposed to be written more carefully again. Okay, so in that case, the next term is this j pi of some s0. So I'm still talking about history dependent randomized equations, the randomized policies. So here this quantity is basically just sum over all the rewards, right? So this is the terminal reward. Terminal reward doesn't have to worry too much, but okay, fine, let's stay consistent. So there's an expectation, so whatever, if there is any form of randomness, then it's a sum over all the other rewards. By all the other rewards, I mean these ones where t goes from 0 to n minus 1. So I'm basically summing over all of these, and inside this there is a sum over this. So ultimately what I'm saying is this becomes see, the outer part is summation over t starting from 0 to n minus 1. The inner part is the expected reward given this randomized strategy, and we have to ultimately take an expectation over this whole quantity. So this gives us the value function, or this is our problem setup.
Okay. I had a thought experiment. What if reward depends on the histories instead of the current state and
Yeah.
the action? If
Hmm.
it depends on the history, so the same equation we can valid, but now uh, since history evolves, reward might change. And I've seen most of the real life, for example, doctor decide on the operation or MBA admission. It depends upon the whole history. So the reward not only like it's not depend only on the state ST, HT also can play. Like it just thought experiment. What
Hmm,
if we do?
so
Because
in principle, that's a valid question. Definitely, that's a good question, in fact. So in principle, you can always have r sorry, you can always have rt, the reward itself, depend on all of the history. All of the history can include everything, where the actions themselves are dependent on history. But this is a claim. I am not aware of it fully, but my guess is because we have used the history to take our action, and we are allowing the reward to be time dependent, meaning the history dependence that you are talking about might be already there in an implicit fashion. Explicitly, it's doable, but it is very much possible that, just like we saw in this week's lecture, that it might not be necessary. But yeah, it is
mhm, yeah.
definitely a valid point. It can be done.
Yeah, because as you mentioned,
Hmm.
RTST comma mu t,
Hmm.
h of ht. So here you don't have terminal state. So terminal state, let's consider terminal state where the action is not present. So why terminal state should be only the last state possible? Why not the entire history? Because there is no action after taken that, right?
Wait, what? Can you repeat your question?
Okay, so I got this point. Since the entire history is taken consideration to decide mu t, so there is a some kind of HT impact on RT. But when you go to terminal state, can we put H of n instead of S of n?
Okay, so I think this type of an argument might be helpful. So when you've reached the final state, h of n, that is just h of n minus 1, some action that was taken at n minus 1, so u n minus 1 to be more specific, and whatever terminal state you've reached. So the update is only these things. Now it depends on how the r function is defined. That may use this part, that may use the whole of it, or that may just this part may be sufficient. Even it's even possible that only this part is sufficient. That's I think that depends on the kind of problem you're dealing with. So in the example that you just gave of a patient's history being used to decide what kind of an action to take by a medical professional, uh, I think that could be modeled using these randomized strategies. Okay, but I'll keep this point in mind. Can the reward itself have an explicit dependence on HT? What happens if that is the case?
Mm-hmm.
That's your question, right?
Yes,
Okay.
because when I did this thought experiment, I found that that claim right always Markov the history dependent approach will boil down to Markov. It is not coming like that.
Okay.
Yeah.
Uh,
Then I thought a lot. I pinged ChatGPT also, but I thought to discuss because the simple proof was like induction, and it is like you take the final state and then go back. But final state was depend on S of n. last state. Then I thought, what if it's the entire history? And when I pinged that and asked, is it possible? Then ChatGPT gave me example of medical, and it's possible. People are taking this. When
It's
I tried
possible.
by myself, it's not. It's coming like it's not depend on only the like. I need history is very important. If your terminal state or your reward depends on the history.
Okay, let me think more about an example of this kind and what happens. Uh, it seems the theorems that we have upcoming, they'll not hold for a situation where you're talking about reward, which is history dependent, but the actions themselves may be Markov deterministic, or maybe even these ones, the randomized ones.
Yeah.
Okay,
Yes.
I'll think about this, and maybe we can discuss it in the next week, in the next tutorial. Okay.
Perfect. 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 Because this is bringing me a lot like this problem.
That's a fair question. Um, I am actually not aware about it, so it's better I don't make statements that I can't justify. So I'll come back to this next time. Okay.
Yeah. Sure.
We can discuss this as the first thing and then continue with the rest of the tutorial. Not an issue. All right. Let's continue now. So, in such a situation, in case where we are talking about history dependent randomized policies, we can see that certain minor changes need to be done to the reward function. We end up taking the expected reward, and the value function also needs to be slightly updated, and it's the transition probabilities also that will get affected by this. So this transition probability, again, u here is not deterministic, it is randomized, meaning we need to consider what is the probability of getting each of those particular actions. So this just boils down to, let's say we're talking about some ut, then we need to consider the probability of getting to that action ut using policy mu t, with which is history dependent and the history is ht. And since it's over the different actions ut, this will become independent of the ut, and will be left with something that's just where the probability of going to the next state just depends on the current state, in because of this randomization of the policy. Okay. So all of these changes are something to be considered specifically in the case of randomized history dependent policies. In deterministic, none of these things will change. The only thing that changes is we update. So here, this was the Markov version. Here we just update how, what mu k depends on, and we're good to go. But in case of randomized, there are a few more expectations to be taken, a few more simplifications that need to be done. Okay, so now just like we had a dp version or an optimality principle holding in case of Markov, we have something similar coming up here also. But before we do that, we need a few definitions. So one of them is optimizing over the set of all history dependent randomized policies if we are starting from initial state s0. And this optimization is basically starting from time 0 and going all the way till time n. So all of those are done. Here there is no mention of how it is being done. It's just that's what h star of s0 means. Okay. Now let's recall what was something that we saw in the MDP version, the Markov policy version. this is the principle of optimality or the DP algorithm. This is what we were supposed to do. We do backward induction, so we start with Jn of xn, which is just the terminal cost, and after that, for the remaining case, this is what we are supposed to do. So we take the expectation over the stage-wise cost. The stage-wise cost would be something that depends on all of these quantities, and the jk value of the previous thing that was solved for, and at the state xk plus 1. Or we can replace this xk plus 1 by whatever dynamics leads us to this xk plus 1. Remember here the optimization, the expectation was over wk, because that's the only source of randomness in our whole problem. Now the claim is that a similar type of behavior shows up even when we are talking about, or even when we are dealing with, these randomized policies. As in, there is something very much parallel to DP that happens here also. And in this version, the Bellman equation take a form like this. Let me copy this and then we talk about it. By the way, there may be a switching between min and max. Just remember, we're talking about optimality. So this is in the MDP version. That's why it's written as max of reward. So notice what is happening here. There is the stage-wise there's the stage-wise cost, just like a stage-wise cost was present in the Markov version. That is fine. And then on top of that, there is a this component also. And because we are talking about the case where everything depends on the history, there can be many different versions of the history that show up. And just like here we had some sort of a dynamics telling us how to go from state xk to state xk plus 1, here we have some dynamics or some information telling us how do we get the next two things, meaning what are the next two things. It's not some dynamics directly here, and we're supposed to take an expectation over the next steps that we get to, since this is in terms of clear transition probabilities and so on. That's why the this term comes up. In fact, we saw that this type of a version is what we would have gotten even if we were dealing with um, deterministic Markov policies, as in that there will be an expectation over these values, the Bellman values. Right? So the same thing is happening here as well. This is just like a comparison right now. Now, there are a few more terms and definitions that we need to see once. But here, recall again, this is starting at time t and going all the way till state n, or sorry, time n. That is the portion that is getting optimized here. So, jt, ht, once solved for, once optimized for, gives us mu t star. And this will be a part of some pi t star, which we for which we would have already computed the previous ones, and we'd add on this as well. Here these can be history dependent. These mu t's could be history dependent and come in the form of some randomization. All of that can be taken care of in the way this is defined. Okay, so far?
Yeah.
So now, a few definitions. There are so many different J's that we have seen throughout. So more like a recap of what are all of these things. So we defined this J star of S0 just now. This is the optimal value of the whole MDP, where we are just putting one constraint, which is that it's starting from state S0. This guy is the value for a policy pi. Here, the optimal policy would have been already found out. Again, remember this is from time 0 till n minus 1. So it's the whole range. This has everything. This is the DP version of this guy. Or rather, this is the DP version of this guy. And the theorem that was talked about in the lectures was that this optimal value, the optimal expected reward, where you're considering from time t till the end, till n minus 1, what is the optimal actions in that range, that is captured by j star of t of ht, while jt of ht is just the Bellman equation that we wrote before. Point being, just like the previous case, when we talked about jt just being dependent on state, here j's are dependent on the histories, and these two end up being the same thing. This is first point, that whatever we have as the dp version of jt of ht, that once optimized is the optimal value, and it gives us the optimal policy starting from time t till n minus 1, and then one by one things get added on. The second theorem, which is what is more specific to the scenario we're talking about here, is that this h star of t of ht is something that ultimately only depends on s, the state st, and not the whole history. The whole history is irrelevant in two ways. It does not give any optimality advantage, and the only new thing that gets added is the state, and hence that is the only thing that becomes useful, and this was shown using a proof by induction. Okay, so the point here is, if you do this, if you use the Bellman equation, solve this for all t in a backward fashion, what you'll end up getting at each step would be this guy, meaning the optimal strategy or the optimal policy from time t to n minus 1. That's what you'll get, and you'll also be getting the optimal expected reward at that point. And once you've done all of them, once you've solved this for all t, you'll be getting the optimal value function for the MDP itself. And it turns out the optimal value function only depends on first the next point is this thing only depends on j star t of st, and when you've solved this for all t, you'll end up reaching this scenario, because you would have solved from time starting from t equal to 0 till n minus 1, all of it. That's the step-by-step logic of what was discussed. And the only point that needs to be remembered over here is, if the problem that we are talking about has the kind of structure that we have discussed, meaning the reward function is written in this form or this form. This is the additive structure that is there in the expected reward, and there is some transition probabilities to start from a state, take some action, and go to the next state. If we have all of these things, as in we have a standard MDP type behavior, then the claim is that these where is the claim? Yeah, these history dependent randomized policies would give you exactly the same thing that you would have gotten from just a Markov deterministic policy also. The values would actually match. Meaning, if you're able to formulate your problem as a Markov decision process, in fact, the reward is something that is of the form that we have talked about, then you don't need to worry about history dependent policies which are randomized. It is more than enough to just focus on Markov deterministic policies. And that's where our optimal will lie. This getting to a point like this is actually a relief, because if we were to go through all the randomized policies, the set of randomized policies is huge. Having to go through all of them at every time step is a huge task. And this particular theorem says that that's not required. Now you can take an example. So you can take an MDP. I'm not going to do this example in detail, but this is just to motivate the idea. So suppose you take, shall we take something that we had before? Okay. We had some, I'm not writing the values and so on, the transition probability values and the other things, the rewards and so on. I'm not writing any of that. This is just to make one point. So the state space here has three states available to us. The actions are, there are two actions, the dashed one and the normal line. Now if we were to focus only on Markov decision, uh, Markov deterministic policies, or rather we know the number is not that big. The number is what was the number? Let's say
A to the power b.
B, and
n
suppose we were doing it for n epochs, or n was our time horizon,
multiplied by n.
right? That becomes
Mm.
multiplied by n. So this part we knew. This is the size of the whole space of Markov decision, Markov deterministic policies. On the other hand, if we were to focus on history dependent deterministic policies, then how would this number be?
Something very big like a to the power b, a to the power a, b square, because history is there. So
History is there, and history has something. So history has a dependence on s depending on what time it is. So this is till t minus 1, rather this is t and this is a, which is t minus 1. So all of this comes up instead of just being dependent on the action that is to be taken just being dependent on B, this would be something that depends on all of it. So
So first time will be a to the power b, then next will be multiply with a to the power small b,
okay,
and then next will be addition, half point addition,
yeah. So
a b
next will
square,
be AB square till whatever
because
number
we
we're
have
going, right?
two actions.
A
Yeah,
n
right.
minus 1 B n, right? That's huge. And there is, apart from very small examples, thankfully we don't have to do all this. In fact, if we are using Bellman, we don't even have to do this many calculations. We don't have to do a search over such a huge number of policies. So it's an even bigger relief that this is something that's not needed. So if you want to, test this particular idea, so try this out. Plug in the values of transition probabilities. So however you can go from some state S to the next state J, taking an action. I'm gonna write it as mu k of history, however you plan to define it.
But
Take the
just a
rewards.
curiosity, like till now, any mathematical equation or problem or algorithm, most of them we can represent in a matrix multiplication or a linear equation. I'm wondering till now nobody has cracked the way to solve this Bellman equation using matrix way or something because because still it's low, but still Bellman equation solving is very tricky. Like it's
It's
very
very tricky.
lengthy by hand.
It is very lengthy. So there are methods to do it using codes, but it doesn't help to. Okay, so let's go back one step. If you notice, this is true for any kind of Bellman equation. If you notice, this component of the Bellman equation, this is fairly linear in almost everything. These are probabilities, these are J
Mhm.
values, these are just rewards. So this is a fairly linear equation.
But recursion is making very difficult, I
Yeah,
think.
that's because of the presence of this iterative behavior that can come up, the recursive behavior that can come up, and on top of that, you're supposed to maximize. So, in
Yeah.
smaller cases, at least it's possible to do by hand. But as soon as the state space grows bigger than 3 or 4, you'll not even be able to do it by hand. So, you'll have to employ codes. And the codes will have to solve this in different methods. I'll name the methods, you can read more about them, okay? So, the
Mhm.
names of those methods, this is actually extra stuff, so I'll write on the first page only. So, remember we talked about this one, value iteration, which
Yeah.
is exactly this.
Limitation.
But instead of going over K's, first written in the form of MDP, and the second thing not in terms of K, just one round and you get all the optimal things. So that one is value iteration. Um, the thing with value iteration is you have to calculate these J things again and again to be able to make any comments about which one is the best policy that you can take. Instead, we can forget about this J altogether and rather focus on only finding the best policy. Start with something random and
Okay.
then try and get to the right policy. That's the core point. How they do it is not something I'm going to get into. There are two or three algorithms which are standard textbook algorithms for this. Uh, I remember only one right now. It's called Harvard's uh, policy iteration algorithm. So you can look it up. So these are two. There is one more which is using linear programming. For us, doing it by hand, solving these bunch of linear equations with max in front and with recursion can get tricky for us, but there are programs that can actually do it. So linear programming is a standard technique. So you can use any LP software and try using it. It's not that hard.
Okay. Okay.
So Yeah, these are three methods. For if you want to know the details of these methods, you can look at Sutton and Bartow. This is one of the textbooks that I am aware of. There are definitely more, but this is a standard textbook if you're interested in algorithms for MDP. This is, I think, called Intro to RL. But anyways, if you just look for the name of the author, you should be able to find it. It's fairly famous. So this is some reference.
Yeah, these are legendary authors actually.
Exactly. Almost everyone knows these this guy. Okay. So if you're interested, you can refer to more of these things. If you have
Yeah.
noticed so far, this particular course is not talking about algorithms that much. There's only one algorithm, and that too is just the core idea of the algorithm that gets used in different problems, and it's possible to solve them. In reality, that algorithm is not enough to solve uh, an actual real world problem. Optimizing that uh, j value function or that j equation is actually really complicated if it needs to be done that carefully every single time. So there are
Mhm.
smarter, trickier ways of making that step faster. That's what happens in these types of algorithms. This one, or this one. LP is something that is the most intuitive one in the sense it just writes. It's the most abstract one. That's more like it. Yeah, these are slightly more intuitive. Policy iteration is actually quite nice.
Okay.
So you can have a look at these different algos, and maybe this will give you a better understanding of how people deal with it. They don't go by solving Bellman equation. That is not the way. Okay. You remember
Yes.
we tried solving for a very simple example in one of the tutorials. Just one example took us more than 1 hour or so. So
Correct.
these are tricky. These are tricky
Correct.
and can get very complicated very quickly.
Yes. I'm very like prone to error also.
Prone to error, yeah. If your recursive relation you've not written it correctly, or the recursive value that you're putting is wrong, it gets scaled up very badly and the sort of error accumulates. So yeah, it's very important to do it carefully. Okay, where were we? So yeah, this is what I was trying to tell you. What you can do is, for this type of a problem, in one of the previous tutorials we solved using value iteration, I think, and we got the optimal states. Maybe it was for this MDP or something very small, very teeny tiny MDP, so we know exactly which is the best Markov deterministic policy to take. Now what you can try out is, first of all, randomize it. There are two policies. There is policy number one, so sorry, there is action number one and there is action number two. You just say policy one says, or first guy's policy is, let's say when you see S1, it is to decide with what probability you're going to take action A1. So let's say with some probability P you take action A1, and with some probability 1 minus P you take the other action. That's a randomized Markov policy. And try finding this. You've written for mu S1, right? Mu1, just mu S1 for now. And similarly you can have for mu S2 also. Maybe that is something that depends on some q, 1 minus q, a1 a2, stuff of this kind. Okay. What you'll see is, if this is what you use, the j you'll get using this particular pi, this particular policy. Okay, you can let this be time dependent if you want it to be time dependent. If you don't want to be time dependent, let it be a constant thing. And when you solve for this, for both the states, so for all xk, you'll see that this will be always less than, in the best case scenario, it will be equal to what you would have gotten if you were just minimizing over Markov deterministic policies. This is a general fact. Most of the times, you don't get a benefit of randomizing over actions. That's the same thing. You can extend this further and try out what happens if, instead of taking a policy of this kind, so this is a Markov randomized policy, MDMR, you can have a HR type of policy, define the history, take a few number of steps, and then repeat the whole process, and you'll see similar pattern will emerge from there also. Which is star S0. Okay, so these are things you can try out. If you have your main MDP solved for, then you can make comparisons using any random policy. You can choose any random Markov random policy or any history dependent random policy, or even just history dependent deterministic policy, and you can see the difference. You'll be able to see what range it will lie in and so on. Okay,
Okay.
so I'll not talk about this anymore, because this, the kind of computation you have to do, you've seen the needed components so far, so I'm assuming you can do all of those things on your own in a fairly easy manner. Let's focus on the next part, which is quite important, and I want to spend more time on that part. Okay, so now, up till now, we have talked about control problems or MDPs where the state was visible. In reality, the state is never really known to us. It is some observation about the state that will be known. For example, you remember you just gave the example of patient histories and so on. The Typically, what is done is, a patient comes, they come with a bunch of symptoms. So those symptoms are the observations. Based on those observations, based on those symptoms, the doctors decide what kind of test they should do to get a better understanding of what might be the underlying disease. So the underlying disease is the true state, but we have no knowledge of the true state. All we know are the symptoms the patient came with, and then on top of that, the kind of tests that were performed. And after having done those tests, then the doctor is supposed to decide which of the possible disease it could be. And there they try to optimize between two things. They're trying to make sure that the health is not something that is taken for granted. The patient's health is maintained or improved, typically improved if they're coming with some problems. And on top of that, they wouldn't want to try something risky or some harmful or strong medication unless it is absolutely necessary. They go with a conservative approach for a certain time, and then they decide what to do if they need to try something else or not. So, a problem of this kind. So, the problem that I'm describing is slightly different from the one that you were talking. Here, it's that there is an actual disease that a patient has, but that disease is not known to anyone, and the doctor is trying to figure out what that disease is. If that disease is correctly figured out and proper medication is given, adequately optimized to what is required, what is appropriate for the particular patient in question, then there is a certain kind of a reward, which is basically improved health. So, such a problem can also be mapped into this setup of MDPs, but here there is one more layer, the layer of observation, and that changes a few things. So, what is happening here is, typically, what the kind of examples that we've seen, we would have a state and then some action taken, the next state, then some action, and so on. That's how we'll get the history. But right now, the kind of example we are talking about, for example, this patient type example, here the history is not so simple. The history includes the true state, but that is not known to anyone. It's only when it is diagnosed correctly that the true state would be known. Otherwise, the true state is not known. It's just a set of symptoms. So those set of symptoms or those observations are what are characterized by this ZK, Z0 and ZK. Just 1 second. Yeah. So these types of problems in the control community are called imperfect information uh, control problems, or imperfect state information. In the language of MDPs, these are called partially observed MDPs, because the state is not completely observed. So before we talk about more examples of this, let's just write down what were the formal things related to it. So just like in the previous scenario, we have some dynamics, right? So the dynamics would be some xk, uk, wk. This is the true dynamics. But remember, the xk or xk1 is never observed. What is observed is these are the observations. So these observations would be some function, um, okay, doesn't matter, that depends on definitely the actual state, and some noise. Similarly, zk would be something that depends on um, so zk would depend on the true state, this noise, and the action taken. Here all these three things are noise terms.
Is it really required, VK?
Hmm? Yeah.
Because I was that in the portal, there was a book mentioned, Vikram Krishnamurthy, who has this partial observed MDP.
Mm-hmm.
So I downloaded that book and I was watching his lecture.
Okay.
He told this as a noisy observation or a noisy sensor and all these things.
Correct.
But when I thought is like VK is not required, like H0 to XK, H0 of XK also could be a model, right? An observation of XK.
It can be.
Then why it is necessary to VK?
Because we're talking about a general setting. So an explicit noise uh, does it for us, right? So
Okay.
it could be something like this also. So suppose this is a different example. So maybe your xk's is a realization of some Gaussian, okay? So it's something sampled from a Gaussian distribution.
Then it may not be finite, no.
Let it be, let it be. It's some real number. So it's a real number
Okay.
that is distributed. So right now I'm not worried about it too much. So let's say this is just R1. Now what I do is I have some operator act on it, some H operator, linear operator act on it. Let me call it HK then.
Perfect.
And I'm assuming that this H is not invertible. So maybe it's better to generalize it and take RD. Okay. So this HK might be some n cross d dimensional matrix. And I'm saying this HK
Okay.
is not invertible. I did not add any noise. All I am doing is I'm just transforming whatever realization I got. But I can't recover it
Wow.
anymore. Did you follow?
Nice. Yes, yes, yes. This
So
could
now
be
I
a
can't
model.
recover
Yes.
it anymore. at least not directly. But this type of a change, a multiplicative change, is a little difficult to handle a lot of the times. So people generally prefer having an explicit noise added, or even sometimes multiplied, because HK is more like a multiplication only. It's just more difficult to deal with. It's different kinds of models, but the the true xk is sort of hidden in some or the other way, that cannot be inferred in any way. It cannot be inferred completely. That's all it means to have noise. Now, it could be directly in the way the model is defined, maybe something like this: we have not added a noise, or maybe we've added a noise, or we've multiplied with a noise. All of these
or
are
maybe
different
both.
scenarios, but the same point. Okay.
Okay.
So, this is sort of an example of noise, noisy system, rather noisy observations.
And small correction, this H0, H0, it will be X0 and V0.
Ah, right. Thank you. Yes, yes, yes. Of course. Right. Okay. So next thing is to talk about what is the cost. The cost is just some guy which is okay. The cost is the same. We're not that worried about it. The only difference is the what the expectation is over. This is k0 to n minus 1. I hope my handwriting is readable enough. My
Yep, yep.
k's and n's start looking the same if I'm writing fast. Okay. Now, the only thing that has changed over here is what the expectation is over. In the previous case, the expectation would be typically over just WK. But here, the expectation would be over a couple of things. That needs to be defined more carefully, but roughly we can say it will be over the VK, all the source of randomness. It needs to consider all of them. So it's VK, WK, and to be even fair, we don't even know what XKs are. It's hidden to us. So the expectation will be over that also. So we are assuming that it is coming from some probability distribution. It's some sampled values, and we'll be taking expectation over that also. This is typically what is done over here. Okay. Now, if you recall, in the very beginning, in the first lecture or so, we talked about information being of a huge importance. So now that will start playing a role here, as in what is known at what time in the problem, and depending on what is known to who, the rest of the problem will be defined accordingly. By the way, do you remember I had given you an example of helicopter helicopter trying to hover
Yes.
at a place that can be mapped as a MDP. To be more accurate, sometimes those readings of what state it is in, what height it is at, what position, what coordinates, all of that depends on the sensors it is using to get those values. So if there is any error in them, it's not a true MDP, it's more like a POMDP type problem, but it's okay to approximate it to an MDP. So if you look it up, there is work dealing with the same problem, but modeling it to an MDP and then talking about the rest of the things. How that helps talk about it in a slightly careful manner. Alright, let's come back here. Yeah, so now we are talking about what is the information at any given point of time. So the information IK is, or rather, let's start with I0. What is known when? I0 means the first observation is known, nothing else. So after I0 is known, the next step will, so for example, I1 would definitely know Z0. It would know the next observation. No, okay, actually, it would know the action taken at U0 in the previous time step, and it will know the next observation. So this is almost like a history thing now. I is pretty much like a history, but instead of having the S term, this has Z, the observation. So at any kth time, I can write this as, let me do it this way. Ik is whatever is known in the previous time step, whatever is the information ik at the previous time step, that along with that the action taken and the new observation. So what is all this? We'll come to this. So this is starting from Z0, it goes all the way till Zk, and then starting from U0, it goes all the way till Uk minus 1. Notice this part, okay? It goes till Zk in observations, but Uk minus 1 in actions. So this is the same idea as histories. Now, the word Markov is not very accurate unless I say things more precisely, but one possible kind of policy could be this way. So this is one type of policy where the policy depends on the information ik and gives us something deterministic. So this is a deterministic policy. Now before we go any further, just notice this thing. Because the true state xk at any time k is not known to us, any added information is actually of value. Hence, a pure Markov thing, as in mu k that depends on, for example, zk, may not be the best choice. So I'm using the word Markov here in a rough sense. So this word will come up again in a slightly more careful way of talking about it. Do you follow what I'm saying? Because zk is a noisy observation, any additional information on top of that, as in what action was taken after that, what was the next observation made, all of these are important information. We can't discard that and just keep the current one, because we don't know if the current observation we got is any better than the previous ones. Maybe the current is the worst observation we have and the previous ones were the correct ones or more accurate. If that happens and we stick with Markov type policy, we'll definitely not be able to get the optimal in the true sense. Hmm? So that's why this is what will be typically talked about, and I'll not talk about this part any further. Okay, so this is not that meaningful. Alright, then our policy would be of this kind, meaning for all mu 0 to mu n minus 1, and what we would be trying to do would be very similar. We would be trying to what happened here? We'd be trying to optimize some right. We'd be trying to optimize some cost function where this is the terminal cost, this is the other cost. This cost, now you notice, has dependence on vk also. That's the general framework. Remember the
But at
expectation.
Excel we don't
Hmm?
write x of n like x subscript capital N.
Mm-hmm.
We would not be able to know right perfectly.
No, no, here it's not about knowing a state. We don't know the state, but the environment knows. And on the basis of that, it's giving us a reward.
So direct reward we know, we don't know x.
Yeah,
Then expectation will come over xn.
exactly. Expectation will come over all x.
Okay, okay.
That's what all the randomness in the problem needs to be taken the expectation over.
Yeah, understood.
Okay, so let's just go back and talk about what is the sequence of steps that is being followed to understand like what is known at what point of time. So let's say we are at time k. The true state is xk. This is the true state, okay? But this is not observed. Nobody knows this state. As in, this is like a realized value from some distribution. Using this, an observation is made by a sensor, most likely a noisy observation, which is zk. This is known. So this is not known. Then next, okay, so let's just take one step back. At the previous time step, we would have known this much. We would have known what is ik minus 1, uk minus 1, what was the action taken, and the observation. Right, so now at this time step, I uh, oh wait, how have I written ik so far? Oh, okay, I've already written it down, never mind. Okay, so this is the information at the current time step, and if you want to understand what is ik minus 1, that is, we can write it more explicitly. So it starts from z0 till zk minus 1, and it is u0 till k u of k minus 2. uk minus 1 is the action that would have taken us to this state, but that happened in the previous time step. So now this part is done. The information is chosen. The next step is the action. So some policy will get us the action, and this action will be uk. Based on this action, the next state will be realized, and the cycle repeats. But this is still not known. Even though we don't know it, this is something that is internal. On the basis of this, a reward will be given. So this is reward rk plus 1. It depends how we've defined it.
Just a thought, if reward is invertible, we can take xk and uk, but it may not be possible.
Typically, it's not. Reward will give. See, you'll be able to infer something from the reward. Meaning, if a particular action led to a good reward, that must be a good state wherever it reached. That's all you can say. It's also possible that you would have ended up with a good reward, but you're actually in a bad state and the reward was maybe just a error in the environment's reward system for maybe just that time step. So that's not reliable information still. Okay, so the thing here is, this we've already talked about. So the thing here is, the action needs to be dependent on ik. Now ik looks very similar to history, right? But there is a reduction possible. The reduction is this is just z0, right? This is the ik plus 1, the information in the previous time step, the action taken in the previous time step, and the observation made in the current time step. Now this can be treated, this part can be treated as a new state. This is still the action. This is the source of randomness for us now, because the noisy term exists in this part. So remember, when we talked about noise, typically the wk, okay, hold on. So this is very similar to having a dynamics in a simple MDP or control type problem. We had a dynamics.
But their dimension was not changing. Here, dimension is changing.
Yes, dimension is changing. That means here the state space was the same. It didn't have to be. The state space could grow, that's not a problem. But what actually would happen is, because the state space would grow so quickly at each time step, this is gonna be exponentially difficult to handle. Anyway, so the point here is a simple comparison between this ik plus 1 and xk plus 1 is, this looks like a dynamics addition of two more information components, two more details about whatever happened in the problem leads to the next state, and this can be used quite nicely, where uk is the same in both the scenarios. Ik is behaving like the state, the new state, which means all that is left is the randomness component. But if you recall, most of the times we assume that this wk's are IIDs, or at least independent of each other. Now what happens here is, these z's have dependencies. The dependencies are as follows. Zk plus 1 is an observation made at time k plus 1. You can look at this diagram above. So if this process repeats, the next will be zk plus 1. So zk plus 1 depends on the action uk and the information, and the previous is more like a history for it, the previous observations, because we know the previous observations were dependent on their respective true states and the actions taken then and so on. So the way this randomness comes up in the problem is that these zk's are now only dependent on ik and uk, and it does not need to depend on the previous observations made. Is that okay? The claim, the next claim is that even though there is a Markov type Markov type behavior between zk plus 1 and the previous observations given ik and uk is known, the dp algorithm still holds in this setup. All we are trying to do is we're trying to go back to our dp algorithm, right? That's the reason why we are talking about a reduction of the space. We're talking about the reduction of the problem in the sense that this is what we're referring to as a state. If this is the state, this is the action, this is just the source of randomness. Right now the only argument is, even though the randomness has a Markov behavior, conditional Markov behavior, the DP algorithm actually still holds even in this setup. Hmm.
Uh, I don't know, but this seems very tricky.
It
Is it?
is.
It should be I of k plus one or k?
Oh wait, that looks like a typo.
Okay,
Uh,
because I k plus one, if you consider,
that's probably a typo. I can just confirm. Hold on. Is the example?
because that probability I'm considering, because I k plus one has information of z k plus one.
Correct, correct, correct. It should not
I
have.
believe,
It should not be ik plus one. It should just be. Yeah. Yeah. Right. Yeah. You're right. Yeah. Good observation. So
okay.
this should not have this plus one. This was a typo. Meaning, this is the part that is not important.
Yeah, now makes sense because it's that intersection with I k will match, like it
Yeah.
is there. Because if you consider I k plus one, no, z k plus one also there.
Correct.
So this
Correct. Correct.
probability.
That was a typo. Fair enough. Fair enough. Because there are so many k plus one here and there. Indices are up and down. No, so that was just it. Nothing more. Um, but yeah, good catch. So this means that we have converted most of the components of the problem to a standard MDP. Even though this was a POMDP type of a situation, but we've managed to make arguments to talk about conversions. The next thing that we have to consider here is what would the DP algorithm even look like. So this component is just as it is from the lectures, nothing I'm adding here. I want to go through this a little quickly so that we can take an example and try at least working out some details of it. So the expected cost would be, one of the terms in expected cost is the stage wise cost, right? So you notice our WK is basically the observation ZK, and ZK has a conditional Markov behavior. So that conditional Markov behavior needs to pretty much show up here, which means this is how uh, this is how we would deal with it. This is basically using okay, I don't recall the name of this property. This is a property of the expectation.
Jensen,
Hmm? No, not Jensen, not Jensen. Uh,
conditional expectation.
the conditional also shows up, something like that. So this is, let's say, conditioned on x. So this is x, this is y given x, something like this.
Okay.
You can check this is a standard property of expectation, that if you condition on something, you can take the expectation of that inside and then do the original expectation outside. Okay. So this term is something that can be rewritten as this g tilde thing, and now it looks pretty much like the way we had it, and because we have already taken the expectation over the randomness in our problem, that gets taken care of, and this becomes the expected cost, and the terminal cost will have to be dealt with in a similar way. So the idea of DP here is, we don't start from the terminal, we start one step before that.
This logic I did not understand in the class. Like why?
Should be conditioning on all the information and the action. There is no action to be taken.
Correct, but information is there, right?
Yeah,
Till
but
n minus.
at that stage, so if you recall in our sequence we talked about this, right? The observation is done after we get the state. If we have already reached the terminal state, there it doesn't make sense to have an observation because we're not taking any action anyways. So it actually stops here. There is no zk, there is no extra randomness involved anyways. So that term is just it, whatever is the terminal cost.
Okay.
Yeah. So now same thing, the same DP type structure is repeated for n minus 1, where we're trying to find out what is the action to be taken at n minus 1, where gn of this state is to be calculated, so that's the terminal cost, but for the particular realization of these x, u and w, and then for the kth state we calculate the stage wise cost, and it's supposed to take an expectation over the condition that we know I n minus 1 and the action so far, and this quantity is to be minimized over different actions. This is the core DP algorithm, just written in the current framework, which is using this conditional component. The conditional component is coming because of the way our randomness is. Our randomness is Markov, conditionally Markov. So that conditionality needs to come up. Okay. Then in the lectures, sir took an example and went through the details of that example, how to solve for such J's and so on. If you have any doubts, we can go through this part, else we'll go to the next example.
Next is fine because this is very manual actually.
This is very manual. This is very manual. That's true. This is, it's just some algebra, basic algebra that you have to just sit and do carefully. That's about it. It's very time consuming for each of these information IKs, but the optimal policies that
And probability to get
are nice.
there.
The probability.
And I don't know because the probability to get answer in first step is very low for me. It's very manual and in
Yeah.
all the cases.
Yeah, you have to practice it a little bit. try different variations of the same problem. So if you want some ideas of the things that you can try out, um, where is the problem setup? Right, it's a machine repair problem, right? So it started out with two states and two observations about the state, whether good or bad, and then what kind of a action could be taken, whether to continue or stop. And then stop had a certain behavior, as in something continues and it goes back to the original state, and there is cost involved in all of these things. So you can try, the simplest situation is you can try varying these probabilities. Varying these probabilities, does your idea of the optimal policy at the end change at all? That's one possibility. Another
But
is going to be a little harder,
mm,
but you can try increasing the number of states.
no way,
Okay, if not
no way.
states, then increase the number of actions.
Okay,
There's continue, there's stop, but you can always have a flag saying, okay, this needs more observation or inspection, or just an extra
okay.
state observe. If you add that extra action, then what happens to the MDP? Like, what is the next state possible? So that needs to be done a little carefully, but you can try out such variations and see. But the idea will remain the same. You'll have to do pretty much the same kind of calculation, and you need to do this kind of calculation a few times on your own. Only then you'll get comfortable with this,
Okay.
because most of these manipulations over here, this part, this was the core thing, right? The
Yes.
probabilities. This is something that is just using uh, properties of probabilities. Not even too many, just one or two simple ones. Bayesian
There
and
was a
yeah, it's actually Bayesian.
there was a point. If you see the second equation of the second page,
Second, this one.
yeah, in the first part, there is a two part on the plus. The first part,
Okay.
okay, where and inside the first part, the middle quantity.
Hmm.
Yeah, so actually when sir was presented, I tried by myself, but I took this probability is equal to 1. Why? Because mu 0 is equal to S, which means I did stop and repair, then Z1 should be good.
That's the
I
thing. That's the thing. When you're doing these calculations, you're not supposed to use extra logic on top of it. You're supposed to use the
Oh,
information given. If that information leads to probability 1, then you take probability 1, otherwise you don't.
okay.
Because
Okay.
when you're doing these things, you'll directly jump to, okay, if you've stopped, that means this is the next step you would go to. It doesn't necessarily, might not be what actually happened. Because see, in this, the way this problem is defined, after stop, it is sent for repair, it's sent for inspection, and if needed, repaired. After the repair, it is back to the good state. It's only in the next time step that we see what happened, but in the meantime, there's one assumption here, I think it was mentioned very clearly, but nevertheless, the repair happens instantaneously. So there is still a lot of time for the next state to evolve, meaning from the good state it can still go to the bad state. There is still a finite probability. I think the number was one third or one fourth, something. So there was a finite probability. So you can't assume that this is where it will stop, because the way time horizons are considered is very specific here. This was just more like a detail in the way it was defined. The repair was immediate, meaning if you decided to stop, because you would have decided, so it's like saying in the previous time step you would have decided to stop for the previous action. Okay, so here you saw some previous state, you decided to stop. Then before you even reach this state, whatever happens because of the stop part would have already happened, and you would have reached the next state. Repair would have led it to a good state, but then the continuation would not stop. That's the way the problem is set up, meaning you would go to the next state, and you can go to either of them with some probabilities. So yeah, you have to you have to you have to be careful that you've understood the actual logic of the problem. If the problem allows you to not have to worry about time this carefully, then it's fine. This should have been 1. But in this particular case, it's not.
Okay, got it. Basically, Z0 is equal to G could have been done 1, but it's a Z1. So it could be
It's a
anything.
Z1. It's a Z1, and
Okay.
it's an observation on top of it. It could have gone to any of the states and then an observation. So yeah, see, that's why Sir decided to add on where it could have gone to. It could have gone to both of them. There's a finite probability of going. Remember, there are finite probabilities for this.
Okay, because initially I calculated, I put it 1 and the answer came very easily. But when I saw the lecture, I found no. So,
So did you try
okay.
putting it this way? Were you getting the same numbers? Uh,
Yeah, now
you
I'm
should.
getting it, but
Okay.
previous logic was I applied 1 directly there.
Ah, maybe that's just because of the numbers in the particular question. Typically, you should be
Okay.
careful.
Okay.
Yeah. All right. So the point was, after all of this, the strategies or the policies that you get are fairly straightforward. So now let's try a different example. We have limited time, so I'm not sure if we'll be able to finish, but let's still try. So this is very similar to one of the assignment questions. I've changed a few things slightly, so you get to have one more question to try out. You can add on whatever you want. So here my dynamics is this way. In the way I've defined the dynamics, I've not added a term. I could in principle add a term here. Then the observation is made. The observation is the part where a randomness gets added in the problem. And this VK is something that I've chosen to be IID, and the probability of getting each of those values is half. The values are minus 1 and 1. And let's just focus on a few time steps. So let's start from 0 to and stop at 2. Okay, the cost function is simple. Cost function is quadratic, and we're taking the initial state to be z0 equal to 1. Oh, okay. Let's try this out on our own, not have anything written. Added extra information. There's no terminal cost. This is still part of the description only. Okay. So if you recall, this is very similar to the linear quadratic problem, that the example that was taken last time. So in this example, because there is an extra component of observation, that adds to the complexity of the problem. So let's see if we can use DP in this type of a setting. What else? The action is 0 or 1. Xk can be any real number. Well, if I'm giving you Z0, the values are sort of defined, but okay, that's still a part of real number, so let's not worry about it too much. So let's start. So the idea would be to define what are the information at each time step. Then
Here, minimizing or maximizing.
we can do either. I did not write right. Uh, let's minimize.
Okay.
Okay. Anything else required in the description of the problem? Okay, let's start. So, so since this is still DP type algorithm, we know that there's nothing to be done for I2 of the J2 of I2, because we are taking the terminal cost to be 0. So this part is simple, but we still need to calculate what is J1 of I1 and J0 of I0. So this part will take some time. So let's first write down what is all of these things. So let's start with I0. What was I0, or what is I0 in this problem? I0 is just the observation.
It's one. It's one only.
Okay, let's not put the value, but yeah, it's actually 1. It's Z0. Z0 is equal to 1. What is I1? Just the things that are needed, the symbols, not the possible values. I1 is Z0, U0, and Z1. Right? It's gonna grow a little every time. And I2 would be Z0, U0, Z1, U1, and Z2. Okay. Next part would be to find out, or at least start by writing out these equations. What is j of I1 and j0 of I0? So so we are going to be, the only thing that we have in control is the u, and this time it is u1. Value of u1 and u0 is 0 or 1, so that part is straightforward. And we're supposed to take expectation. We'll write it carefully. Expectation is over what? um, our cost function is, okay, x1 square plus u1 square, right? And we need to consider the previous term, j2 I2 as well. And we have to put the conditional. The conditional is I1 and the action u1, I guess. Is that correct?
Yes section.
Let's just verify once. Where is the core definition? Okay, this is correct. So this is the core definition, right? So for jk ik, you're conditioning over knowing ik and the action uk. Alright, so where were we? So this is correct. We've conditioned on the right things. So now let's just be slightly more careful about this. So what do we know up till this stage? We know z0, we know u0, we know z1, and from here we know u1 also, when we're trying to solve for this guy, when we're trying to optimize this guy. So let's write down a little bit. Let's see how much further we can get. So now what is the source of randomness up till this point?
X1 actually, but X1 no.
X1 is something
Here
that
randomness is, here randomness is not there, right?
there is VK, no? There's randomness in the observation itself. So VK is,
But in equation is not there any VK or ZK.
okay. Right. So we can write, because we know ZK, we can write it like this. So the
Okay.
the randomness in VK is transferring to XK, or you can think of it the other way around. So technically you were right in saying that the expectation is over X or XK of that time, but ultimately it turns out to be dependent on VK only. So I can write this as the probability of each of those VKs is half, and the two values are 1 and minus 1, right? So that's z1 minus 1, z1 plus 1, that's why. This term does not have anything to do with randomness, so nothing to worry about here, and this term is 0. Okay, so now this is what needs to be optimized, but we don't really know what are the possible values of z1 and so on. So okay, let's hold on, as in how do we calculate this for different u's and all of that. Let's come back to this again. Let's write the same thing for the easier case, which is j0 I0. Here we are minimizing over u0. Same thing. Now this matters. So we know x z0 is 1, so we can write this as 1 minus 1, which is just 0, so there doesn't have to be this term. But okay, let me write it carefully first and then go to all the other stuff. Okay, so z0 minus 1, j1. I want to write this more carefully, okay? So I'm gonna start writing u1 now. I'm gonna use this type of a notation. So there is z0, u0 and z1. Okay, let's wait for a minute. Okay. Or okay. This term does not contribute when vk is 1. z1 minus vk becomes just 0. So we're left with this. And on the other case it matters, so z1 plus 1, sorry, z0 plus 1, which is just 2, so it's 2 square plus u0 square, and this guy is as it is. This is something that we need to do very carefully, so I am not writing it yet. Z0 So notice, because z0 and u0 is known, the only source of randomness is the value of z1, and the value of z1 depends on what kind of v1 would have been encountered at this point. So we'll have to consider those possibilities and take care of them. Those are the ones that will get included here, not the ones that depend on v0, but rather the ones that depend on v1. Okay. now we need to finally solve for j1 of I1. Only then we can plug in the values and solve for j0 I0. So let's try that. uh, okay, let's start from here. Z0 is 1, which tells us something about what x0 could have been. X0 could have been either 0 or 2 with equal probability. The reason why I need the previous step is only then I can make a guess as to what the next one could be. So from here, let's say an action is taken. Let's choose the action to be 0. If 0 action is taken, then xk plus 1. So x1 would be, this is, what are we taking? Okay, just adding them. So it's just either 0 or 2. It's based on this that the observations would be made. Right? Here is when V1 is playing in effect. Here it was V0 that was playing in effect. So the possibilities are, uh, these are the values of Z. Z1 could be -1 or 1. Z1 could be, oh, achha.
Yeah, the possibility.
Those are the possibilities. Both of them are with equal probability. And here the possibility would be Z1 could be,
1 and
huh, oh, 1 and 3. So we need to look at all of these cases. Now notice the probability of having any of these, because of the simplicity of this problem, all of these are just with probability 1/4. Fine?
why 1/4? 1/2, right? Like 1 by 2.
Uh, so the
Okay.
way I've written it, I have used this V0 also. I've used what might have been the actual X0 value, which would have led to two
Okay.
different values, and probability of this and this is equal. It's just half. Assuming that this is
Okay.
the action you've chosen, this is the observation you had. And then if you want to find out what is Z1, any of these values are of same probability, right? Half of this, which ends up being 1/4. You can do this more carefully the same way Sir did. It should turn out to be 1/4.
Okay.
Okay, so that means this is one scenario. We've only done one scenario. The other is if the action taken was 1. If the action taken was 1, x1 would have been 1 minus 0 minus 1, and hence z1 could be 0 or -2. Wait, am I adding or subtracting? Oh, I'm adding. Sorry. 1. This would be 0 or 2. This would be, this is 2, so 1 gets added. 3. Again, with same probability. Now what we need to do is we need to plug in all of these possibilities of z1 values and simplify this. Since z1 itself can take so many values, uh, we need to consider all of these cases. So z1 when I1 um, I1 is 1 0 and z1 is, let's say, minus. When that happens, you're minimizing huh something seems wrong here, right? When you want to minimize over u1, okay, anyway, ultimately you're supposed to minimize over u1, so you will take in these values and plug them here. So it was -1 squared by 2. Oh no, it's fine. uh, so you can see that since we're trying to minimize, u1 equal to 0 is the one that will minimize this. Similarly, you'll do it for other values and you'll be able to find what is the minimum value. So if u1 is supposed to be 1, then the minimum value of this is just 2. j1 of 1 0 minus 1 is this. Then once you have all of them, you would have solved for this j1 of I1, and since you would have solved for all of them, all the possibilities, you have to just take care of these scenarios. Then just take the expectation of over them and plug all these things, and you should be able to solve for j0 of I0. Is the process clear? I don't think I can solve
Yeah, but
the remaining
it's
in
very
time.
long actually. You need to do.
Hmm?
The process is very long and
It's
you
very
need
long.
to do.
It's very long. That's true. And you have to do you have to do all of this very carefully. Otherwise, it can get tricky very quickly.
Okay,
If there is just one error, the error will destroy everything else.
properly.
Yeah. So try and finish this on your own. Consider that as a practice. If you
Okay.
encounter any problems, or if you notice that something was not clear, you can ask me next time. Not an issue.
Yeah, that probability 1/4 I try. At least that I want clarity.
Uh,
I'll try by myself.
this one.
Yeah, yes.
Okay.
Because
Try
how
it.
do we represent with symbol and then reach into this? I don't want to do mistakes which I did there.
Fair, fair, fair. Give it a try, and let me know.
Okay.
Okay. Um. All right. Do you have any other questions?
No, except this history as a reward dependent history. No.
Yeah, reward dependent history. I'll look into that. and we can discuss that first thing next time.
Mm-hmm.
Okay, so let's, yeah, yeah, you were
Yeah.
asking something, go on.
And one thing, this just a curiosity only. There is no need to proper answer.
Mm-hmm.
I'm wondering on this transition probability and the noise we are equating, right? So from information theory point of view, like I am from that background, uncertainty and randomness. These, because one side is a randomness which is noise, uncertainty which is transition probability. So in information theory point of view, we need some more logic to be equate. Like we can't directly equate. We need to describe entropy, we describe mutual information, all these things to equate these two. Like it's not very straightforward to
Mm,
equate.
we're not doing a straightforward equality. We're saying that these two formalisms are can be used to describe the same problem. It's just two different frameworks. One framework talks about there being an explicit randomness. Another doesn't talk about randomness. It talks about some transition probabilities.
Yeah, some uncertainty. We
Yeah,
don't know.
yeah.
Hmm.
So it's
Okay.
like saying in one I'm talking about the presence of a random variable, and the distribution is underlined. In the other one I'm talking about the distribution on the states instead of that noise factor. That's the difference. So because we are talking in these terms, we still don't need to use information theory type terms like entropy or mutual information or any of those,
Okay.
right? That's the only reason. If we want to talk about specifically what information is available from a particular random variable, then that's a different question altogether.
Mm-hmm.
So far we've not tried dealing with that kind of a term. Okay.
Okay.
All right,
Yeah.
let's take a quick recap. We talked about mainly two things today. One, the first point that we made was if we have these history dependent randomized policies and we were to write down the optimality condition, the Bellman equation, and so on, we find that from this set of history dependent randomized policies, the optimal that we would get, the optimal value or the optimal policy that we'll get, will have a one to one correspondence with a deterministic Markov policy. Okay, meaning the optimal Markov policy ends up being a policy that is Markov deterministic. This was the first point that we learned today. And then we talked about situations where this may not hold. For example, when the state itself is not known and there is a noisy or a partial information about the state, as in some imperfect information is present. When that is the scenario, so there is some noise that masks the information in some or the other way, then we call such problems as either POMDPs or imperfect state information. And in these types of problems, the set of information that we have, all the previous information, which could be observations, which could be actions, all of that is important because we never know whether the current observation we made is that reliable enough. Like, on top of the observation, we need some sort of a quantification that tells us, okay, this is this much reliable, hence you should only use this. Since we don't have that by default, we can't really use only one information and not and discard all the previous information, the observations. Which is the reason that in POMDP type problems, it's typical that you look at the full range of IK, the information available. Uh, but at the same time, we can convert the problem, we can convert this problem and make it look like a standard MDP problem by saying that this IK can be considered as a new state, and in that sense, the observation, which is noisy, which is one source of noise, can be similar to our disturbance in the state dynamics. And even in this situation, DP can be applied. And one problem was solved in class, the lectures, and one we tried right now. The one that we tried right now focused on a linear action, linear state dynamics, and there was this observation, which is the component that had a additive noise, and we tried solving for it. We didn't manage to finish it. It's fairly complicated and fairly long, but once you go through it, and you'll know for each I1 which is the optimal strategy and what is the optimal value, and hence once you have done it for the whole thing, there might be a clearer and simpler answer. And same thing can be applied even for the previous time step, which is